SwayamPrabha. Digital India. Educated India.
A logical and systematic approach to solving organic chemistry problems to CSIR-NET exams. In module 19, we will be looking at asymmetric synthesis, mainly methods of asymmetric induction using substrates, reagents, catalysts, and the reactions controlled by these reagents. I am Professor Balaji, currently working at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, currently Ministry of Education. So what we will learn in this particular module or this session is we will be looking at various reagents, catalysts that are used in asymmetric synthesis. So let us look at the first problem. So this problem was asked in June 2011. The major product formed in the following reactions. We have a allylic alcohol that is given here, and this is treated with tertiary butoxide. Tertiary butyl hydrogen peroxide in the presence of titanium isopropoxide, and the catalyst or the diethyl tartrate is a chiral induction ligand that is used in this reaction, and it is having a plus enantiomer is used in this particular reaction. So we end up with the 4 different products A, B, C and D, and we have to find out what is the right product that will be formed. And if you look at the combination of these reagents are generally used for epoxidation of allylic alcohol. So this is called as a Sharpless reagent, and this is mainly used for the epoxidation of allylic alcohol. So that means if you look at A, B, C and D, product C and D has the alkene unit also underwent epoxidation reaction, but tertiary butyl hydroperoxide oxidation in the presence of titanium metal does not oxidize the alkenes. So we can rule out C and D as our final product. So we have only A and B as our expected product in this particular reaction. And the only thing is, what is the enantiomer that we are using here, that is the diethyl tartrate salt which we are using here, and what will be the obtained products to stereochemistry. So these are all the 2 things we will have to understand. Once we understand that, it becomes very easy for us to predict what is going to be the product in this particular reaction. So if we look at what is the product that will be formed in the reaction, is the first one is we have a prochiral allylic alcohol. This undergoes enantiomer selective epoxidation reaction. So when we use the plus DET, that is diethyl tartrate isomer, this facilitates the oxygen transfer from the bottom phase as shown here. So how do we actually know what is this product this is? We have to draw as a square is shown here on the right hand side. So here in the bottom right corner we keep the hydroxy unit. That means the allylic alcohol is drawn in such a way that the hydroxy unit is on the right hand corner side, and then we rewrite the entire molecule with the corresponding substituents that are present here, and then rephase, that is the bottom phase, is the place where the plus isomer, the diethyl tartrate salt, whenever we use the plus isomer, that attacks this allylic alcohol's double bond from the bottom phase. So when it attacks from the bottom phase, we end up with the oxygen from the bottom phase. So this is a enantiomer selective reaction, and this is a very, very specific reaction. So in this particular reaction, the isolated double bond does not undergo reaction. So this is the one thing we have to remember, and the overall reaction is nothing but Sharpless epoxidation reaction, and Sharpless received a Nobel Prize in 2001 for this particular and related reactions. So the importance of this reaction is use of the plus isomer leads to the bottom phase where the oxygen is introduced, the epoxy oxygen is introduced. And let us move on to the next problem. So here the major product formed in the following reaction sequence is the starting material has a alkene unit, and this is treated with BH3, borane, THF, and hydrogen peroxide and sodium hydroxide. So oxidative reaction workup is actually carried out. So nothing but what the first step of reaction is hydroboration reaction followed by oxidative workup. So this is the first step that is happening. And in the second step, triphenyl phosphine DEAT, that is diethyl azo dicarboxylate, is the reagent that is used with 4-nitrobenzoic acid. So what is this reaction? This reaction is basically a esterification reaction. That's the only thing we will see. And then there is a specific name for this reaction, that is called Missionobu reaction. And the specificity of Missionobu reaction is inversion. That is the only thing we have to remember. When the alcohol is converted to the ester, the alcohol's stereochemistry is inverted in the product. So this is the one thing we have to remember in solving what is going to be the product. So the second step is nothing but the Missionobu reaction. And the third one is potassium carbonate methanol. So the potassium carbonate methanol is a combination which is generally used for the cleavage of ester unit. So what we are actually doing here is we have an alkene. The alkene is converted to an alcohol, and that alcohol is converted to an ester, and the ester is hydrolyzed to the corresponding alcohol. So this is the overall reaction. During the esterification reaction, inversion takes place. So these are all the only thing. And based on that, we are going to find out what is the final product. So here, if you look at A, B, and C, and D, all the cases, we have the hydroxy compound, and all of them has the hydroxy unit, and all of them have a methyl unit. So the only difference is whether they are pointing upwards or whether they are pointing downwards. Both are cis orientation. In the other case, one is pointing up, another one is the methyl is pointing up and the hydroxyl is pointing down, or the methyl is pointing down or the hydroxyl is pointing up. These two are trans products. So we have two sets of product. One is A and D are the cis product, B and C are the trans product. We have to find it out which one is actually formed in this particular reaction. So the first step is the diastereoselective hydroboration reaction. So this reaction, in the presence of borane followed by hydrogen peroxide, sodium hydroxide oxidative cleavage, leads to the corresponding alcohol as the final derivative, and this is a syn addition reaction. It's a stereospecific syn addition reaction, and it follows the anti-Markovnikov rule. So once this is formed, then what is the next step is basically the esterification reaction. So in the esterification reaction, the inversion takes place. So the hydroxyl's stereochemistry is inverted in the final product as the ester, and the final step is the hydrolysis of the ester, which leading to the liberation of the hydroxy unit. So the ester hydrolysis gives the hydroxy derivative, and this is the final product that will be formed. So in this case, the methyl and the hydroxy group are in the same position, cis orientation. So the next problem is the major product formed in the following reaction is we have again an allyl alcohol is given, and this is treated with PHC hydrogen peroxide derivative is given. Cumene hydrogen peroxide is the compound that is given here. So the cumene hydrogen peroxide followed by reaction with the titanium isopropoxide, that is a metal catalyst, and 1.2 equivalent of DIPT. So instead of diethyl derivative, here we have diisopropyl tartrate derivative. So the enantiomer what we are using is the minus enantiomer we are using, and the reaction is carried out at minus 20 degrees centigrade in DCM solvent. So this question was asked in December 2015. So we are going to find out the sets of product what actually will be formed. So we have a allyl alcohol. So we can assume that the allyl alcohol may undergo epoxidation. So that is one. And the presence of minus isomer will give one particular enantioselective epoxide. So that is one thing. And then what will happen is each this is a racemic compound. The starting material given here is a racemic compound. It will have actually two enantiomers, A and B, let us say, and one of the enantiomer may undergo epoxidation, another enantiomer may not undergo epoxidation. So in other words, the epoxide product will be isolated as a separate enantiomer, one of the product, and the other one which does not undergo reaction is recovered from that reaction. So we end up with two sets of product. One is the alkene converted to the allylic alcohols double bond converted to the epoxide. Other one is the starting material which did not undergo, one of the enantiomer that did not undergo the product, or the two things which will be formed in this reaction. So here various combinations are given, and based on these combinations we are going to find out what is the final product that will be formed. If you look at all the cases are more or less similar. In one case, one of the enantiomer, that corresponding allyl alcohol, did not undergo reaction, in which case the hydroxy group is pointing away from the observer, and in other two cases the hydroxy unit is pointing towards the observer. So this is one set of product, and the other one is epoxidized products are also formed. So epoxidized products are basically the diastereomeric product. So we have various combinations that are possible. So based on that, we have to identify what is the actual product that will be formed. So let us assume, before we work out the product, we will have to assume that we have two enantiomers which are present in 1:1 equivalent in the reaction mixture. So that is what we are going to assume. So the starting material can be written as two enantiomers, A and B. And once we have these two enantiomers, one of them will undergo the reaction in preference to the other one because of the steric reason. So we are going to see which isomer will undergo fast reaction and which isomer will undergo slow reaction. So the top isomer will undergo fast reaction. So here the hydroxyl is pointing towards the observer, so this undergoes fast reaction, and the other one, because this particular substituent that is present on this particular carbon basically, and this hydroxyl unit, they are actually on the same in the opposite side. So that is the reason this reaction does not, if the epoxidation has to happen, what will happen is this alkene bond has to coordinate with the metal center. That is point number one. Then this hydroxy unit also will actually coordinate with the metal unit. So these two has to happen. Then only the epoxidation will actually takes place in the next step in the catalytic cycle. So because of this presence of this bulky methyl, paramethoxyphenyl group, what happens is this hydroxyl cannot now coordinate with the metal center. So that is the reason this bulky paramethoxyphenyl group prevents the tight coordination, or the hydroxy unit, the metal and the alkene in a formation in the catalytic cycle, which prevents this from undergoing reaction. But in the other case, the methoxy group, the paramethoxyphenyl group is far away from that. So the alkene, metal and the hydroxy, all the three can all directly be coordinated to form the required complex in the catalytic cycle. So that is the driving force for this reaction. So in A, the epoxidation is possible, whereas in B, the epoxidation is not possible. So finally, what we know is once the coordination happens, the DIPT will come and attack from the top side. Then we actually end up with the final product. So that is the reason the epoxide is actually formed as shown here, and this is the product that will be formed in this reaction. And then the unreacted, the other enantiomer will be isolated. So that way we can exactly know what are the two products that will be formed in this particular reaction. So the enantiomer B will be recovered, and the top one is the epoxidized alcohol that will be formed. So let us move on to the next problem. So here the major products A and B formed in the following synthetic sequence. Here we have a alpha beta unsaturated system that is given here, and the first reaction is phenyl magnesium bromide and copper iodide. So this is a cuprate addition reaction followed by acidic workup in the next step. So introduction of the phenyl group is going to take place in this particular reaction, and that is going to give an intermediate A. So let us say this is 1, 2, 3 and 4. We have A and B, two types of intermediates that are possible. A is the intermediate, B is the final product. And the intermediate A, which is formed after the cuprate addition, is treated with the sodium ethoxide followed by reaction with bromine. So there are two different reactions that may be possible. And then we end up with the compound B. So we have to identify what is the product that will be formed. So if you look at 1, 2, 3, 4, all the reactions, all the intermediate A looks very similar. The only difference is the stereochemistry is the only thing that is different in many cases. So if we go with product B, in all the cases we also have the only difference is the bromination happening at two places or bromination happening at one place. So this is the only difference that is present, and of course it is very difficult to identify whether which reaction will actually proceed. It's very difficult to say that dibromination is possible, but monobromination may be happening. So maybe 1 and 2 are most probably the product and not 3 and 4, because 3 and 4 has dibromo derivative. So they may not even form in this particular case. So we can rule out 3 and 4. And now we have to figure it out whether it is 1 or 2, which is actually going to be the right product. So let us look at what are the reactions that will happen. So the first reaction is nothing but the 1,4 cuprate addition. So the phenyl magnesium bromide, the negative part, the nucleophilic part, which is the phenyl unit, adds across the double bond. So this is nothing but the 1,4 addition as we mentioned earlier. So the phenyl group adds here, and finally the hydrogen actually will add here, and this will undergo ketoenol tautomerism to give the final product. So the final product is actually when this particular intermediate is formed, the oxygen is now having a negative charge. So we have two types of attack which is possible. The phenyl group can attack from the top, or phenyl group can attack from the axial position or equatorial position. Those are all the two things. So this is the axial attack and this is the equatorial attack. But the equatorial attack has a problem because here we have a methyl group and there is a phenyl group. So they both are sterically in close proximity. So those attack is not possible. And moreover, in A, we may have a very small 1,3 diaxial interaction, but that is very small compared to this 1,3 allylic strain in the case of methyl group. So this 1,3 allylic strain is very high compared to 1,3 diaxial strain, because in the other group we only have hydrogen atom. So the 1,3 diaxial strain may exist in A, but it is not very high compared to the 1,3 allylic strain because of the bulky methyl group. Phenyl group and the methyl group, they are in close proximity. So steric because of the steric repulsion, this particular intermediate is actually not formed. So then we only have the top product, that is the A may be formed in that first step, and this one on hydrolysis leads to the corresponding derivative where the phenyl group is in the axial position. So as you know, the phenyl group in the axial position may still have some amount of 1,3 diaxial interaction. So what happens is the ring flip actually takes place. The ring flip takes the phenyl group to the equatorial position. So in this case, the phenyl group is pointing upward, the acetyl unit is also pointing upwards. So in other words, these two are in the cis orientation. Remember, this compound also has the 1,3 diaxial interaction because we still have hydrogen atoms here, we have hydrogen atom here. So they may interact, 1,3 diaxial interaction may exist in this compound. So again, what we can say is this may not be the thermodynamically stable product. So then under basic conditions, what happens is the one of the hydrogen atom is abstracted by the ethoxide anion. So that leads to a enolate anion. So this enolate anion can now undergo protonation to give the corresponding derivative. So here if we look at the phenyl group and the acetyl unit, both are trans to each other. In other words, we do not have the 1,3 diaxial interaction that is happening. So all these reactions are basically called as epimerization reaction. So the epimerization of the axial ketone leads to the ketone in the equatorial position, because here there is no 1,3 diaxial interaction, and hence this product is more stable compared to the starting one before the epimerization. So this is a very crucial reaction that happens in the presence of the base. So once this is formed, then what is the next step? The next step is bromination reaction. So the bromination occurs on the methyl carbon. So one of the hydrogen is replaced by the bromine atom, and we end up with the bromo derivative. And as we have seen here, the phenyl group and the acetyl groups are trans to each other. So this is the only product where we have the trans stereochemistry between the adjacent group, and this is the final product that will be formed in this particular reaction. So let us move on to the next problem. So here a major product is formed in the following reaction sequence. This question was asked in December 2015. So we have a allylic alcohol. So this allylic alcohol undergoes 3 different reactions. One is a metachloroperoxybenzoic acid reaction. So we will see what is this reaction, and then the next one is basically it is nothing but the epoxidation reaction. And sodium acide and methanol, that is the second step that is happening. So when we treat a sodium acide with the epoxide, what happens is basically the epoxide is opened up. So this is the next step that may happen. And the third step is triphenyl phosphine and acetonitrile combination. So the triphenyl phosphine acetonitrile combination reduces the acide to a primary amine. So this is what happens. And we have a amino alcohol. So we have a hydroxy unit here, we have an amine there. So this amino alcohol may undergo loss of water molecule to give a acidine. So that is one of the things which is shown here. And here also if you look at A, B, C and D, C and D have the free amine group that is present, and A and B has the acidine that is present. So under the reaction conditions, this can easily undergo cyclization reaction. So that is what is the clue you have to remember to solve this problem. So in other words, C and D are not the right product, because if we stop with the triphenyl phosphine reduction, then we will obviously assume that okay, we are going to have a amino alcohol as our final product. So this is the expected product. But then under the reaction condition, what happens is nitrogen being more nucleophilic in this particular case leads to the next step, the loss of water molecule to give the acidine unit. The only thing what we have to find out is what is the stereochemistry of the acidine that will be formed. So let us start with this reaction. So the first reaction is nothing but the epoxidation reaction. So this is a very crucial thing in deciding what is going to be the final stereochemistry of our product. The reason is the presence of this hydroxyl is very crucial in directing the introduction of the epoxide. So generally MCPBA based epoxidations are not very stereospecific, but most of the times what it happens is the attack actually takes place from the less hindered site, and peroxides are highly stereospecific epoxidation reactions. So in that case we have only one double bond. So this one double bond is supposed to undergo epoxidation. So we will get, since the hydroxyl is a bulky group, let us assume that, so it is pointing downwards. So the epoxidation is supposed to take place from the opposite side, but that is not happening here. The reason is the presence of hydroxyl group actually helps in the hydrogen bonding. So this hydrogen bonding is very crucial, and due to this hydrogen bonding, the epoxidation happens from the same phase of the hydroxyl unit. Unlike the normal cases where there is no hydroxyl, the epoxidation takes place from the least hindered site. But when there is a hydroxy group that is present, and then which can actually form a hydrogen bonding, then what actually happens is the epoxidation happens from the same phase of the hydroxyl unit. So this is a very important thing we have to remember. Once we remember this, then solving this problem becomes much easier. So now we have fixed the stereochemistry of the epoxide. So once we fix the stereochemistry of the epoxide, what is the next step? The next step is the epoxide opening by the acid anion. So acid anion, as you know, it is a SN2 reaction. So this will come and attack the epoxide from the opposite side of the leaving group. So what is the leaving group? Here we do not have a separate leaving group, but it is nothing but opening up of the epoxide that is happening. So the acid will come from the opposite side of the epoxide. So in other words, the acid is now going to be from the top phase. The hydroxyl is now in the bottom phase, because in the initial epoxide itself, the epoxide is in the bottom phase only. So this SN2 attack is very similar, and the next step is the reaction with triphenyl phosphine. So the triphenyl phosphine actually converts the acid into a amine, and here there is no change of stereochemistry. So the acid stereochemistry is retained in the product also. So we end up with the amino alcohol. So the next step is a crucial one. So this leads to loss of water molecule. That means the lone pair of nitrogens on nitrogen attacks this particular carbon with the hydroxy group is lost. So that leads to the formation of the aziridine. And since the amino group is from the top phase, the aziridine is also formed from the top phase. So that way we can actually fix the stereochemistry of the final product, and then we can exactly say this is the final product that is formed in that reaction. So for the entire process to happen, the presence of this hydroxy unit is very, very crucial. Once the hydroxy unit stereochemistry is known, based on that we can actually build the entire molecule. So let us look at how this reduction of the acid with the help of triphenyl phosphine happens. So the resonance structure of the acid is actually written here. The lone pair of electron on the phosphorus attacks one of the nitrogen atom. Then it leads to the phosphoruside intermediate, and then that intermediate actually loses a nitrogen gas, and the loss of nitrogen gas is the driving force for this particular reaction. That leads to the iminophosphorine derivative, and the hydrolysis of the iminophosphorine derivative gives the primary amine. So this is how the acid is actually converted into the corresponding amine derivative. And of course this overall reaction is called as a Schrödinger reaction. So let us move on to the next problem. So here the intermediate A and the major product B formed in the following reaction sequences. There is an epoxide that is given here. This is treated with phosphorine derivative, and that leads to the formation of an intermediate A that is treated with butanol at -78 to room temperature, leading to the formation of another final product B. This question was asked in June 2016. So 4 different combinations are given for A and B, and if you look at all the 4 combinations, let us look at B alone. In one case we have a trans isomer, another case we have a cis isomer, here also we have the cis isomer, here we have the trans isomer. So in other words, the alkene that is formed in the second step, 2 cases are cis isomer, 2 cases are trans isomers. then how do we even know what is actually the right product? So this is little bit complicated. The only thing, a clue given in this particular reaction is minus 78 degrees centigrade. When the reaction is carried out at minus 78 degrees centigrade, we need to know whether it will facilitate Z isomer or the E isomer. In other words, the cis one or the trans one. Low temperature generally prefers the cis isomer, so that we will see. So the first step is reaction of the epoxide with the lithium phosphorine. So this phosphorine actually opens up this particular epoxide from one side. So we end up with a trans reaction, because this is nothing but a nucleophilic ring opening SN2 type mechanism. So that is the reason whichever direction it attacks, the oxygen goes to the opposite side. In other words, the relative stereochemistry of these two groups are going to be trans to each other. So that's the only thing we have to remember here. So once it is opened up, then the next step is this reaction is basically the non-stabilized Wittig reaction. So in this Wittig reaction, the non-stabilized halide is used in this reaction, that leads to Z-alkene, because the reaction is carried out at minus 78 degrees centigrade. So this is the one thing we have to remember very carefully. When the reaction is carried out at low temperature, Z selectivity is the most important one that is being formed. And then finally the product what we are going to get is only having the cis geometry or the Z geometry in our final product. The lithium derivative is actually hydrolyzed to give the corresponding hydroxide derivative. So with that we can exactly say what is the relative stereochemistry of these two carbons. These are trans to each other. And what is the stereochemistry of the alkene that is formed? It is the Z isomer that is formed.